Welcome to example number 9. Now, in the previous example, example 8, we learned that you could calculate the mass of a stationary object such as a planet where you have different satellites that are orbiting around it. And if you know the orbital radius r and the period t, then you could determine the mass of the planet. So in this example, we do not want you to calculate the mass of the planet. We're going to give you some information about two satellites, and using our telescopes, we have determined that they have an orbital radius of 48,000 kilometers, the first satellite, and the second one is 64,000 kilometers. Now, from earlier investigations, we know that we have a satellite named Charon that is orbiting at 19,600 kilometers with a period of 6.39 days. So what we'd like to know is what is the time period for the first satellite and the second satellites that were discovered back in March 2006. So let's write down all the given information that we have here. So for Charon, which is the known satellite, we have a period and radius given of 19,600 kilometers for the orbital radius. We'll call that R1. And then the period for that particular satellite is 6.39 days. Now, for the other two small satellites that were just recently discovered, we know that the first one here, we'll call it R2, is at a distance of 48,000 kilometers for its radius of orbit. And the other satellite, we'll just call that R3, is a distance of 64,000 kilometers. So what we're trying to find here is what is the period for these two satellites, period 1 and period 2 and period 3. So we need to find some relationship between the radius of orbit and the period. And hopefully you realize that's really Kepler's third law. Let me just quickly recall how to derive Kepler's third law using Newton's second law. We have mv squared over r for the net inward force, and then we have Newton's universal gravitational law, g m1 m2 over r squared. And so then we get gm all over r equals the velocity squared, which is 2 pi r all over period squared. And so we get the next line here, 4 pi squared r squared all over t squared. And let's rearrange for t. So t squared would be equal to 4 pi squared, now r cubed, all over g and m. So hopefully you'll see that for all these satellites that are orbiting around Pluto, they all are orbiting around the same planet, Pluto. So this m is the mass of Pluto. 4 pi squared g and m is the same for all of these satellites. So you could write an expression like this for each satellite as they orbit around Pluto. So ideally, we don't want to use the mass of Pluto. We don't want to discover. I suppose you could take these two pieces of information and then find m, but what we want to do is not have to determine the mass of Pluto. What we want to do is use ratios. If you were to write, for example, T2 squared all over T1 squared, and T2 squared, let's say, is this expression, 4 pi squared R2 cubed divided by g and mass of Pluto. And then for T1, it would be the same expression, except what would change is just the radius, R1 cubed divided by g and the mass of Pluto. And so essentially the 4 pi squares cancel out, and the gm cancel out, and you get T2 over T1 squared for both of them is equal to R2 cubed all over R1 cubed. So T squared is proportional to R cubed. And so I suppose you could just jump to there. But you really do need to explain that this came from Kepler's third law. So now, if we're solving for T2, it would be equal to, well, T2 squared would be equal to R2 cubed all over R1 cubed, and then this is being multiplied by T1 squared. So if we're solving for T2 by itself, we would take the square root of this whole thing, So we'd square root this and square root this, and we would get R2 all over R1, the ratio of that, to the power of 3/2, because that is the square root of something that's cubed, multiplied by T1. So if we look at the first satellite, we would get T2 equals brackets R2, that's 48,000 kilometers, all over R1, 19,600 kilometers, to the power of 3/2, multiplied by T1, 6.39 days. And you'll notice that I didn't change my kilometers to meters, because I would have meters and meters on the top, and it would still be the same thing. So there's no need to multiply the top by 1,000 and the bottom by 1,000. It'll still be the same thing. And then again over here, I just want days. So there's no need to actually changing these back to your regular SI units of meters and seconds, unless you were having to determine the mass of the planet. And so if you put this into your calculator, using the power of 3/2 here, you'll get 24.5 days approximately. So that first satellite that was discovered is 24.5 days. And now let's move down to do part B over here. T3 would be a similar expression, except we're going to write T3 over T1, always comparing to the known satellite that we're given. So T3 would be comparing its radius of orbit, 64,000 kilometers, to Charon's radius of orbit of 19,600 kilometers, and this is to the power of 3/2, multiplied by the period for Charon, and that is 6.39 days. And so once again, put that into your calculator, and you will get 37.7 days. Okay, and so now you know how to determine the time period of different satellites or moons that are orbiting around planets without actually needing the mass of the planet itself. And that's it for this example.